Hi, it gives me great pleasure to take you through this video to explain the magnetic field of a solenoid. A solenoid is nothing but a number of coils or rings all stacked up. You have already seen an animation on the magnetic field of a coil or ring, so that should be helpful to you while going through this. And as usual, when we go through a solenoid, which is a stack of rings, when there is no current, there is no magnetic field. So let's now start from scratch and see what's happening. So we take a battery with a positive and negative terminal, connect the positive to one end of the solenoid, which is right here is the top of it, and the current will flow all around it, come right down to the bottom and flow back through that blue wire into the negative of the battery. So this is to explain the physical arrangement. Let's look at the animation now. Initially no current, and then you have a current, which is represented by the white arrow. The white arrow goes all around the coil. Meanwhile, you have some magnetic field, magnetic lines of force set up instantly the moment the current starts flowing. The little blue arrows that are going around the lines of force are only to show the tangent to the lines of force at any point. The magnetic field does not rotate by itself, it's stationary and it's a static field. And the arrow direction shows which should logically be the North Pole and which should logically be the South Pole. So the end of the solenoid where the lines of force have a direction of coming out is like a North Pole of a bar magnet, and that end of the solenoid where the lines of force have a direction as if they are going in, that's the South Pole of the solenoid, same like the South Pole of a bar magnet. So now you get a feel that the solenoid is acting like a bar magnet, and that's a good finding. Looking at this sketch in more detail, this is just to convince you that the right hand thumb rule applies all along the wire. So when the current comes in, and that's a white arrow again, you see all these small yellow rings that are plugged in there. They are imaginary rings of the magnetic lines of force. So if you put your thumb around that, you will feel that the down arrow is on the inside of the coil, on the inside of that solenoid, and the upward arrow is on the outside of the solenoid, which means all the down arrows are accumulated inside the solenoid and point downwards, giving a concentrated magnetic field that's pointing downwards. And on the outside, it's a much weaker field. This is the reason why solenoids became popular, to concentrate and focus a magnetic field inside of their diameter. If you look at this sketch in detail, it's a kind of side view of the envelope of the magnetic lines of force. This sketch is just to show that the magnetic lines of force are elliptical, looking like a butterfly. Now why is that so? So since we saw that the downward lines of force are all concentrated inside the solenoid, inside that diameter, obviously they repel each other because they are like very similar directions. So they repel each other, so they push themselves sideways, and because of the sideways push on the magnetic lines of force, they all get spread out sideways and you get an ellipse that's elongated. So, and that's the reason why you don't see exactly concentric circles of magnetic field. In this particular sketch, you see that the magnetic lines of force is kind of cropped. This is a textbook representation because you don't have space to draw all the lines of force that are really big. And this is just a few lines of force to represent the magnetic field. Of course, the magnetic field is 360 degrees all around this coil, and if you draw all the lines, it would be very crowded indeed. Let's now look at the equations that govern the numbers. So you have the B vector, and as per the Ampere's law, the magnetic circulation, which is B into L in this case, will be equal to mu 0 times the net current that's flowing through the coil. The net current that's flowing through the coil is N number of turns per unit length into length. So that's basically n by unit length into length, so that becomes a quantity without a unit, into the current. So the current I is the one that's flowing through each turn, and the turns are helping to magnify the effect of the magnetic field. And that's why the solenoid is useful. You put more turns, you get a higher strength of the magnetic field for the same current. So that is the equation for the vector B is mu 0 n into I. That's all there is to it. Let's look at a typical numerical to get a feel of the numbers. So here is a coil that's 50 turns per centimeter of solenoid length. The person needs an output of 0.05 Tesla out of this solenoid, and the question is, how much current do we have to input into this solenoid? So we just plug in the equation that we know. We have a straight equation, and we have three things that are known to us, and there is only one unknown, so that should not be very difficult. In fact, it's very easy, as we will see. So B is 0.05 Teslas. That's equal to mu 0, which is 4 pi into 10 to the power minus 7. Number of turns is 50 per centimeter. That means 50 by 10 to the power minus 2 meters. We have to take care of those units, and I is the thing that we have to find. So plug in these things, cross multiply the numbers, and you will get that I is 7.96 amps. That's a neat little problem, and that gives you kind of confidence that you can work with the numbers on a solenoid. Thank you very much, and I hope this was useful to you. Have a great day.